Hello everyone, I'm Kishan Agarwal. Today I'm going to present my AAT Tech Talk of Embedded Systems, and my topic is Smart Network Interfaces for Advanced uh, Automotive Applications. So before going to the topic, let us discuss a brief introduction about it. Computing in vehicles has increased dramatically with electronic control units. Like EVs have been designed, so computing in vehicles has increased to control the electronic units, EUs or ECUs, communicating over increasingly complex and heterogeneous networks and presenting challenges in scalability, validations, and security. So we are going to describe the concept of smart network interface, incorporating programmable computation at the network layer to enable hardware level fault tolerance, application consideration with sufficient isolation and system level security. So we have seen that how the automotive networks have been evolved from simple single protocol system to complex multi-domain network. So what are the modern requirements? Real-time performance, scalability, and security. These are the few reasons. So traditional ECUs face limitations in handling these requirements efficiently. So we'll discuss what are the challenges which are faced in the automotive networks. First challenge is of the scalability. More components and connections strain network performance. Next comes our validation, ensuring reliability across complex systems. That means validating different uh, devices or components in a complex system. That is validating is quite difficult. Security. This is the main important aspect, that is protecting in-vehicle networks from cyber security threats. Like automatic driverless car or a vehicle which can be hacked or the security breach may occur. So some of the functionality may not be go as it need to be. So these all aspects are very important, and this poses challenges. So what are smart network interfaces? A network interface that integrates computation for handling real-time data. That is incorporating programmable computation at network layer to enable hardware layer fault tolerance, application consolidation with sufficient isolation and system level security. So what is the purpose of it? To enable efficient fault tolerance, secure data handling, and application consolidation. Offloads processing from ECUs processes to network layers. So let us compare how these traditional ECUs are different from smart network interfaces. So traditional interfaces only handles data transfer, lacking capabilities for real-time data processing. Next comes is smart interfaces, integrate programmable processing, monitoring, and security, which we already seen in the definition. So what is the outcome? It is improving our reliability, lower ECU load, and real-time data handling. So these smart network interface do have some components. Let us discuss some of the components like programmable data paths, which uh, provides or enables uh, custom data processing directly into network layer. Instead of ECUs, dependence of ECUs will be reduced here. Security modules provide in-network encryption and decryption for secure communication between components of different smart network interface. And the last one comes the hardware accelerators, which manage data processing efficiently with minimal latency. So to run any type of software hardware interaction, we require some type of protocols. So protocol enhancement is must. CAN plus and FlexRay. So what is this? High bandwidth while maintaining compatibility with traditional CAN, allowing for 16x more data to be transferred. This is CAN plus. FlexRay enhancements, adding synchronous communication for deterministic performance. If the components communication is not synchronous, that is asynchronous, the data which is required before some other data to be arrived may work as it is asynchronously. So synchronizing the communication between the components is very much important. This ensures reliable data flow and synchronization. These are the two important things. So let us discuss the benefits of data processing at network layer. So smart interface manages data before it reaches the ECU, that reduces processing demand on ECU processors and synchronization. Network layer ensures timing consistency across all ECUs. Like some data need to be processed before some other data to be processed. So this synchronization is must to proper data flow within within a vehicle or any type of hardware system communication. Efficient data flow, real-time data processing allows faster response time, that is low latency. Embedded security networks in network interface. These security layers need to be embedded. They are very important. This provides inline encryption and decryption without adding latency. If we are adding separate encryption and decryption algorithms to improve the security, this adds some of the latency in data transformation, which may degrade the performance of the component. By implementing high latency, that is the transmission of data may be delayed due to different encryption models. So inline encryption decryption, which provides low latency, that means minimal latency will be added. Real-time security secures data flow directly in the network, avoiding processor load. And outcome is protects against unauthorized access with zero delay to data transmission. So this embedded security in network interface provides high level of security by providing inline encryption and decryption without any adding latencies, which works by communicating the data from one component to other without any data breaches. That means secures directly in the network layer, and which provides zero delay to the transmission by providing high security for unauthorized access to the devices or components. So let us see a case study. Low latency data packing. Low latency is very important for data to be transmitted from a component to other component for better synchronization and better usage. So the issue is high data volumes from FlexRay to Ethernet creates processing bottlenecks. So these high data which need to be transferred will require high latency. That is the bottleneck. What is the solution? Smart interface handles data packaging, reducing latency up to 80%. This is a very important. This will result in faster data handling for applications like sensor data streaming and other. Case study for adaptive reconfiguration in ECUs. So what is the scenario here? Adaptive systems such as terrain response needs fast mode switching. That means data transmission should be very fast. So how this can be overcome by using smart interface? Reconfigures hardware dynamically without occupying ECU processor, which will result obviously in faster response, ideal for critical applications, while timing is essential. See, some of the applications which require faster response and some other applications may require uh, results, but they are not that time dependent. Some amount of time delays may be accepted. So based on that, the ECU processor occupancy will be reconfigured. Next, we'll discuss the performance metrics and applications. What are the key metrics? First of all, lower latency, reduced power consumption, and decreased processor load on the ECUs. Where all these performance metrics are applied on the real world applications such as driver assistance, infotainment, autonomous vehicle system, AVS, which provide an outcome of overall vehicle performance with the smart network interfaces. SNIs. So in summary, I would like to say that smart network interfaces overall offers scalability, security, and high performance with low latency, and multiple other benefits of synchronizing communication between components and other things. So what may be the future prospects to improve these SNIs, smart network interfaces? That is integration with ASIs and SOCs for enhanced automatic applications. Adoption for smart interfaces in autonomous as well as connected vehicles. Thank you.